Okay, guys, I want to do one more slightly more complicated series resistor problem with you. But before that, I wanted to make a couple observations on the formula sheet. Hopefully you guys are referencing this, and maybe some of you guys already have it all memorized enough to where you're not really having to worry about it too much. But I just wanted us to look at a couple of the formulas here, and they have them kind of split in half for you. So we got the series and the parallel. Now, all the formulas in there are going to be different, except for two of them that are going to be the same no matter whether you're talking about series or parallel circuit. So that bottom one is one we haven't really used in solving any of the equations yet, and that's going to be how to find out what the power is. So when we're trying to calculate for the wattages, regardless of what type of circuit we're doing, that's the only one that's going to be the same formula each time. So we're going to go ahead and look at one more circuit to solve, and with that in mind, I just wanted to go ahead and get that laid out. Because on this one, as you can see, we have wattage values instead of resistive values. And we're going to have to work a little bit backwards to solve some of these. So this is going to be pretty simple, but we're going to have to work backwards a little bit. A lot of you guys might just be able to see you can take the resistor values you have and subtract it from the total and get it, but we're going to do it algebraically just because we want to break it down and make sure everybody can see exactly where we're getting these numbers from. So in this circuit, if you look, we got wattages on everything except for one value, which is going to be for resistor 1, which we have the voltage. So with that, we have the total. We're going to go ahead and put all those values in, and we're going to see if we have enough information to solve for any of these. So for the total wattage, we got 0.768 watts. Let's go ahead and work down the line. So we got resistor 1, we have a voltage instead, 6.4. Resistor 2, we have a wattage, 0.102. Resistor 3, 0.154. And resistor 4, 0.307. So as it stands, we don't have enough information to use Ohm's law on any one resistor or for the total in this. But we do have that rule, that formula that we looked at, which is true for both series and parallel circuits, that if we add all of these resistive values together for the power of each individual one, the power total is going to be this, which we already have. But we are missing one of those. So we're going to have to look at exactly how do we solve for that. So what we're going to do is we're going to go ahead and add these up and subtract that from the total, and that's going to give us our missing value. So if we take 0.102 watts, 0.154 watts, and 0.307 watts, we add those together, we're going to see what we get, and then we're going to subtract that from the total. So that gives us 0.563 watts. So all the wattage values of the resistors individually, except for one, are adding up to 0.563, and we have the total. So what we're going to do is take the total, 0.768 watts, and subtract the rest of those, and that's going to give us that last value that we're missing over here. So 0.768 minus 0.563 gives us 0.205. So now we have the last value, which if you see also gives us two values for one resistor, which gives us enough to start plugging in Ohm's law. So this is a little bit different than the regular Ohm's law because we have a power value here. So we're going to go back and look at our formula sheet real quick and look at if we have power, we have the voltage, we can solve for either the resistance or the current. So if we're looking for the current, let's go ahead and start off with that. We can find that with this formula here. So I equals P divided by E. We'll go ahead and use that one. I equals P divided by E. We have P and we have E, so we're going to find I. So the power, 0.203, divided by the voltage, which is 6.4. And we're going to do our typical rounding to the nearest thousandth. Gives us 0.032 amps. And with that, we can also find the resistance. So let's go ahead and divide 6.4 divided by that new value we got, and we'll find the resistance values there as well. So 6.4 divided by 0.032 gives us 200 ohms. All right, now we'll get a series circuit, and we have all the values for one of the resistors. So one of these is going to be the same across everything. And that, again, is going to be the current. The current in a series circuit, as we can see on our formula sheet, is the same across every single resistor. So let's go ahead and just transfer that value across, and then we'll have enough information to go ahead and solve for all of these. So 0.032 across every single resistor in this circuit. And it's also going to be the total. So now for the rest of these, we have a little different situation. We got the current and we have the power, but we don't have the resistance or the voltage. So let's go ahead and go back to our formula sheet if we still don't have those memorized. And we know that if we have the current and we have the power, we can find any other two value. So if we're looking for the resistance, for example, we have the current and the power, we're going to be using this right here. So R equals P divided by I squared. So R equals P over I squared. So let's go ahead and plug in our values. So the power for resistor 2 is going to be 0.102 divided by 0.032 squared, which gives us, if you round off, 99.609 ohms. Pretty close to 100. All right, let's work down the line and do the rest of those. So it should be the same thing, right? We're just going to take 0.154, divide that by 0.032 squared, which is going to give us 150.391 ohms. 0.307 divided by 0.032 squared. It's going to give us 299.805. And our total, we can do the same thing. 0.768 divided by 0.032 squared. Our total is going to be 750 ohms. So now we're just missing the one value, and there's a lot of different ways to solve it since we have three values in all these categories now. But let's just go ahead and use the most simplest form of Ohm's law, which is E equals IR. So all we're going to take is we're going to multiply the current times the resistance factors, and we'll get the voltage drops across each, and we'll even get the voltage total as well. So for the first one, I'm going to go ahead and take these two values, multiply them together. So 0.032 times 99.609 is going to give us 3.187 volts. All right, 0.032 times 150.391. 4.813 volts, and we'll go ahead and do the same thing down the line. So go ahead and plug all those values into your calculator, and then we'll go ahead and fill those in. Now you're going to notice a couple things if you go to check your work backwards after we've done any rounding, which we have done some rounding here. So if you get any values that are slightly off by a few decimals, don't worry about it too much. If you want to carry these out farther than the thousandth, you can. But if you're using Ohm's law to check your work backwards or adding up any of these, your numbers might be slightly off. Just remember it might be because you did some rounding in there. But we have all the values, and we saw probably the most complicated type of series circuit that we're going to be looking at here. So we're going to start compiling some of these, but this is as difficult as the individual series is going to get. And if you got all this stuff down, then we'll go ahead and move on to parallel with a lot of confidence. So again, we'll see you guys again soon. Hopefully getting tired of my voice because you're going to be hearing a lot of it.